Alright guys, in this video we're talking about 2.5 independence. Okay, so first of all, let's take a look at the definition. So two events A and B are independent if the probability of A given B is equal to the probability of A and are dependent otherwise. Now, let's take a look at example and say how this definition works. Example. So I will say toss a fair die, and I will say that event A is representing that 5 is tossed. So what's the probability of A here? So based on the formula we went over before, we know the probability of A is equal to the possible outcomes in event A divided by the total. And since we're tossing a fair die, so we have 6 numbers in total and only one of them is 5. So the probability of A is 1 over 6. And then I will say, what is the probability that A given an even number? Now, if we have already known that the numbers tossed is an even number, and what is the odd, not even, an odd number. So we have already known that number tossed is an odd number, and what is the probability that the number is 5. Now, if we have already known that, the number is odd, then we're gonna know there are 3 odd numbers in total. So the bottom will be 3, and only one of them is 5. So the probability is 1/3. And actually, we can figure it out through another way by applying the formula of a conditional probability. Right? So we can say that this is equal to the probability that A intersection an odd number divided by the probability of an odd number. Of course, A intersection an odd number is just 5 is tossed over here, so that would be 1 over 6, and then divided by the probability of an odd number. So since there are 3 odd numbers in total, so the probability would be 3 over 6. And if you simplify that, you get 1/3. So in this case, we have the probability of A given odd number is 1 over 3, and this is completely different from 1 over 6, right? Because this odd number here is telling us some information about event A, and that's why this probability is greater than this 1 over 6 over here. And this is the first case. Okay, this is the first case. Now let's take a look at the second case. So I will give you here is that I will see B is representing that good weather outside. Good weather outside. And then what is the probability of A given B over here? It's 1 over 6, right? Why is 1 over 6? Because this event B is telling us nothing about event A here. The event B is telling us nothing about event A, right? Whatever the weather is good or bad outside, the probability of getting a 5 is always 1 over 6. Okay? So since the event B is telling us anything, it's telling us nothing about event A. So in this case, the probability of A given B is equal to probability of A. So this 1 over 6 is equal to the probability of A over here. Now in this case, we will say that A and B are independent. See, just like what we see over here, two events A and B are independent if the probability of A given B is equal to probability of A. So if this happens, if the probability of A given B is equal to probability of A, once this happens, that means that the event B is telling us nothing about event A. That's why we say they are independent of each other. Okay, and actually we can derive another formula. So we know the original a formula of probability of A given B is equal to the probability of A intersection B divided by probability of B, right? And if A and B are independent, we have that the probability of A given B is equal to probability of A. Of course, if A, B independent. If A and B are independent, we have this is coming from the conditional probability, and this is coming from the definition of independence. Now, if we multiply probability of B by both side equation, we're going to have the probability of A intersection B is equal to the probability of A times the probability of B. And this brings us to the proposition down here. A and B are independent if and only if the probability of A intersection B is equal to the probability of A times the probability of B. And this is a very, very important proposition, because that's the way how we determine if two events are independent or not. So if we want to identify if two events are independent, we just need to say if the probability of A intersection B is equal to the probability of A times the probability of B or not. If they're equal, then those two events are independent. If they're not equal, then they're not independent. That's it. Now, once this proposition clear, let's take a look at the example here. The problem says it is known that 30% of a certain company's washing machines require service while under warranty, whereas only 10% of its dryers need such service. If someone purchases both a washer and a dryer made by this company, what is the probability that both machines will need warranty service? And it says that they're independent. So if we translate this question into a form of probability, we're looking for the probability of A intersection B. Since A and B are independent, right? And because over here, A is representing a washing machine needs a service, and B representing a dryer needs service. And we're looking for the probability that both machines will need warranty service. So we're looking for the probability of A intersection B, and we know they're independent. Then we can apply this proposition over here. The probability of A intersection B is equal to the probability of A times the probability of B. What is the probability of A? That's 0.3 times 0.1. Which is the probability of B? So this is equal to 0.03. And actually, there is another proposition I would like to mention is if A and B are independent, then A complement and B complement are independent. Okay, if A and B are independent, and then A complement and B complement are independent. Now, once we know this, based on the example over here, I want you to find what is the probability that neither of them needs a service. So neither of them needs service. That means the washing machine doesn't need a service, and the dryer doesn't need service. So we're looking for the probability of A complement intersection B complement over here. And we know they're independent. that is equal to the probability of A complement times the probability of B complement. So the probability of A complement is equal to the probability of 1 minus probability of A times 1 minus the probability of B. Okay? And what is the 1 minus probability of A? Probability of A is 0.3, so this is a 0.7 times probability of B is 0.1, so that is 0.9. So this is equal to 0.63. So the probability that neither of them need service is equal to 0.63. Okay, so once this makes sense, I have one more question for you. So what is the probability that at least one of them needs service? So what is the probability that at least one of them needs service? So I'm gonna show you two ways to figure it out. Number one, let's just break it into different parts. Let's think of different cases. So that will be equal to. So let's take a look at what does it mean by at least one of them needs service. At least one of them needs service means that it could be the washing machine needs service, but the dryer doesn't. That's number one. Number two, the dryer needs service, but the washing machine doesn't. Number three, both of them need service. There are three different situations we want to think of. So number one, the very first situation is that the washing machine needs service, but the dryer doesn't. So that would be the probability of A intersection B complement. Okay? The A means the washing machine needs service, and the B complement means the dryer doesn't. And plus the second case, A complement intersection B. So this means that the washing machine doesn't need service, but the dryer needs service. And then plus the probability of A intersection B. That means both of them need service. Actually, I will put two more things over here, which is if A and B are independent, then A complement and B complement are independent. And A complement and B are independent. So if A and B are independent, then A complement and B are independent. And the third one is if A and B are independent, then A and B complement are independent as well. So we're going to have three conclusions over here. If A and B are independent, then A complement and B complement are independent. If A and B are independent, then A complement and B are independent. If A and B are independent, then the A and the B complement are independent. That's three different cases. Now we can calculate this over here. So since they're independent, we're gonna have the probability of A times probability of B complement, and then plus the probability of A complement times the probability of B, and then plus the probability of A times the probability of B. And this is equal to probability of A is 0.3 times probability of B complement is 0.9 plus probability of A complement is 0.7 times the probability of B is 1, and then plus probability of A is of course 0.3 times 0.1, and this is equal to 0.27 plus 0.07 plus of course it's a plus plus 0.07, this is 0.37. That's the first way to solve this, to figure out the probability at least one of near service. And there's a second way. So as what I mentioned in the previous video, if we think of the first way, this is quite complicated because we got three different situations to think of. This is quite complicated. But as I mentioned in the previous video, I said that if it is too hard or it is too complicated to think about it directly, we usually think of the opposite of it. In other words, we think of the opposite of it. So once we find out the probability of the opposite or the probability of the complement, we subtract this probability from 1, we'll get the probability we're looking for. Now, let's think of what is the opposite of at least one of them needs service. What's the complement, or what is the opposite of that? So the complement of at least one of them needs service is that neither of them needs service. So this would be equal to 1 minus the probability of neither of them needs service. So that's equal to 1. What is the probability of neither? 0.63. So 1 minus 0.63 is 0.37, which is exactly the same thing as what we got in the first way. So they are completely equal to each other, and those two ways are equivalent. You got the exactly same answer. You will get the exactly same answer if you do it correctly. Okay, so you can do it either way, but I will encourage you to think of the second way because it is very important to learn how to think of the complement of the event. That's a very important skill for solving some probability problems. Okay, that's pretty much all about this question. Okay, now once this is clear, let's take a look at the second example over here. This is an example from textbook 2.35. Each day, Monday through Friday, a batch of components sent by the first supplier arrives at a certain inspection facility. 2 days a week, a batch also arrives from a second supplier. 80% of all supplier 1's batches pass inspection, and 90% of supplier 2's do likewise. Okay. Now it's asking what is the probability that a randomly selected day 2 batches passes inspection. And it says we will answer this assuming that on days when 2 batches are tested, whether the first batch passes is independent of whether the second batch does so. So they are independent. So if we want find out the probability that on a randomly selected day 2 batches pass inspection. So first of all, we get to have that on that day 2 batches arrive, because there are going to be 2 different situations. One is that only 1 batch of components arrive, and the second situation is that 2 batches arrive on that day, right? Now let's take a look at what is the probability that 2 batches received. So if 2 batches are received, that means a batch arrives from the second supplier, and there are only 2 days a week. So we get 5 days in total, and 2 days we get a batch from the second supplier. So the probability 2 batches received would be 2/5. And of course the probability that 1 batch received is 3/5, because there are 3 days that there is no batch from the second supplier. And once we know that the probability that 2 batches received is 2 over 5, and we can try to find out the probability. First of all, let's translate this question here into the form of probability. First of all, we know we're looking for the probability that it got to be 2 received. I'll put it this way. Actually, we are looking for that 2 pass. Right? If we want 2 pass, first of all, it got to be 2 received. And then intersection. So after we have 2 batches received, and then there are gonna be 3 different situations. One is that the batch from first supplier passes, but the batch from the second supplier doesn't. Situation number 2, actually we have 4 situations in total, and what I just mentioned is the first one. And the situation number 2 is that the batch from first supplier doesn't pass, but the batch from the second supplier passes. Inspection number 3, both of them pass. Situation number 4 is that neither of them pass. And what we want is both of them pass. So we're looking for the probability 2 received, intersection 2 pass. That's what we're looking for. Now, once we know what we're looking for, let's take a look at this graph over here. I think this graph will make everything clear. So first of all, we got 2 different situations over here. Of course, if we simplify this to a decimal, it's going to be 0.4, and this is 0.6. Now we have the probability that 1 batch received is 0.6, and the probability 2 batches received is 0.4. Okay, and that's what we want. And then we keep going. Once we have 2 batches received, we're gonna have 2 different situations. First, one is that once we get the 2 batches received, we want to think of if the first one passed or not. So the probability that the first passes is 0.8, and the probability the first fails is 0.2. Okay, and then we keep going to say the second batch, and the probability that the second pass is 0.9, and the probability the second fails is 0.1. And same thing over here. The probability the second batch pass is 0.9, and the probability the second fails is 0.1. Now, what we are looking for? Which situation is we are looking for? Is this one over here. First of all, we want 2 batches received, and we want both of them pass. Okay, and we know they're independent, so this probability would be equal to 0.4 times 0.8 times 0.9. Now let's take a look at this over here. So the probability 2 pass is equal to the probability 2 received, and both pass. And of course, that would be equal to the probability both pass given both received times the probability 2 received, which is equal to 0.8 times 0.9 times 0.4, which is 0.288. Actually, we can get this answer from here, from the graph directly, because we have 3 steps to get the 2 pass, and the probability of the first step is 0.4, the probability of the second step is 0.8, and the probability of the third step is 0.9, and they're independent of each other. So if we want to find the probability of 2 pass, we just need to multiply them together. Okay. Now, what if I want to ask, what is the probability that no pass? No pass. So if there is no pass, it could be only one batch received, and it could be two batches received. Okay, so if we think of only one batch received and we want to find the probability of no pass, we'll say this: the probability of one batch received is 0.6, and the probability it fails is 0.2. So that would be 0.6 times 0.2, and then plus. Let's take a look at the situation when two batches received. So if two batches received, the probability of that is 0.4. And then if we want no pass, that means the first fails, and the probability of that is 0.2 times the probability of second fails, which is the probability of that is 0.1. Since they are independent, we multiply them together, and we'll have 0.12 plus, what is that? 0.08 and this 0.008. Okay, and this is equal to 0.128. And that's how we find the probability of no pass. We got to think of this situation over here, this situation over here, and this situation. Two batches, and the first fails and second fails. Okay. And I hope this makes sense to you. And actually, there is a general form. Events, the definition is that events A1 through AN are mutually independent if for every k is equal to 2, 3, and n, and every subset of indices I1, I2, and Ik. So the probability of AI1 intersection probably AI2 and until intersection the AIK. So that is equal to the probability of AI1 times the probability of AI2 times the probability of AIK. So that means actually we can extend the proposition of independence to a general form. So however many independent events we have, it doesn't matter. It doesn't matter however many events we have. Once we know the events are independent of each other, so the probability of the intersection of all these events is always equal to the multiplication of the probability of each event. So you just need to multiply all of the probabilities together if all the events are independent. Okay, that's just an extension to the general form from the proposition we have up here. So always keep the idea in your mind. If we have two events are independent, then the probability of the intersection is equal to the multiplication of two probabilities. All right, that's pretty much all about the independence.